Alright, in anticipation that many of you have spent, I would call it, an inordinate amount of time to solve simple reactions, I'm going to go through this a couple ways using a setup I've done with different views and layer manager states. So essentially what many of you slid to, I would say, is the slide and divide, but I want to point out realistically, for the most part, the way you really want to do these problems is to compare the size of the circles. If you want to think, instead of force times orthogonal distance, you might want to think just the size of the circle. So I'm going to draw a circle here, shift right click from the end point of there, shift right click tangent to that line there and that circle there, and then another circle, shift right click from the end point and to the end point there. And the ratio between those two circles is our ratio of moment arms. I'll show you how that works. I go from here, from the end point, perp to, and that shows you your moment arms. So you have force times orthogonal distance equals force times orthogonal distance. You do that once, twice, 3 times, and you get it done. You're just looking at ratios of the moment arm. But that said, slide and divide, this is how that first problem would look like. From there you slide that down. Remember, you never want to lose that point of application. You get some distances here and you're looking at just, in the end, right, you're dividing that into components. It's a slippery slope to say that all of that goes out to this reaction here because it's a pin joint, but the pin joint is the only one that can react in the x direction, and so you have basically a ratio of areas here. I'm going to zoom in a little bit. So the reaction at this joint, realize it's going to be less than half of the 4.37, so its distance from the other support, which is about 7.7 times the distance divided by the distance between the supports, which is 20 times that distance, and then you have the opposite there. So that's the first one. Go to the second one. Go back to layer state 1, problem 2. You slide, measure the distance, and divide. Once again, in this one, you knew that everything is going to have to be on, all the y component is going to have to be on the roller joint because it's right on top, but all of this x component comes back over here. Go back to problem 3. Notice me setting up the views to jump around. This problem here, if you're going to do, you want to get the area underneath, place it at the centroid. That really should be slid down there if you're doing your best, but you're going to once again slide, right, measure some distances, and divide. In this case, you realize that the force is very large because the reaction at this support is going to be negative. It's going to be down because you've got a fulcrum right here. So in this case, you have the distance from the other support divided by the distance between the supports, but it becomes a negative number. That is problem number 3. Problem number 4, let's go back to our first layer state. Basically, force times, this one is going to split evenly pretty much between the two, and this is going to go more to that side. Force times orthogonal distance, you could do, if you think about doing this by circles, you have shift right click from the end point here, shift right click to the end point there. You've got one circle there. When you're doing the support about the left joint, circle from the end point there to the end point, and you have the ratio of the circles, of the radius of the circles. That kind of shows you that it goes half, but you have to step back when you're done and look at these things and see that your answers make sense. If you look at something like this, it should have more on this support than on that support. I'm going to go to problem 5. I'm sorry, I finished this one up. 1, 2, in other words, you slide, Once again, mathematics is the same, but you want to get used to putting that point of application actually where, or the tail of the vector actually where the force is applied. Get your distances and do your calculations. I'll go back to problem 5 now. Problem 5, this of course is, realistically, was about changing your coordinate systems. Shifting it, turning it that angle. Once you do that, you slide, measure, and divide. Problem 6. Again, you see this force out here is going to actually cause, after the time you slide and divide, it's going to actually cause a negative reaction out here. You slide, measure, and divide. If you think about this, this one here is approximately maybe 2.4 from the reaction here, so you've got distance from the other support would be the full 15.88. The distance between the supports 13. So you'd have basically a greater force there, and you'd have a negative force over here to this one, but this one counteracts a little bit. Therefore, you get a very minimal reaction there. Back to 1. This is problem 5. We'll go to problem 6. I'm sorry, that's what we just did. Problem 7. This one, most of these are not going to be best solved by slide and divide. I'll give you the example here. If you think about this force here, you can go ahead and do a circle, or I'll do the circle first from the end point here, tangent to that force line there. That gets you your moment arm. If you think about it, this is kind of a torque that could be spinning all the way around. And if it was twisted down, this is where it would come onto that one. That is for if you're using the full amount of force. If I draw another circle here from the end point to these are actually blocks that have insert points, you realize that that's about what, 3/4 of the way, so about 3/4 of that force is going to go over here. However, later on you're going to see you could actually add these two together and make it one force, but in this case we were doing slide and divide. And what happens when you slide and divide, you have to have your lines of force. You measure where they're going, and you slide and divide. And this one, of course, would slide all the way down to there. You end up with the same mathematics. Probably the most correct is to do the idea of torques, however, because that's really what you want to do. You want to start doing these by doing sums of moments. That ties you up into all the other structures you'll want to do. I'll go back and finish the rest of these. This was problem 7, problem 8, slide, measure, divide. Once again, this slides down. Once again, this one going to be easier perhaps just by simplifying into one force by doing some sliding right up here in space. Remember, you can add non-concurrent forces by doing slides and adding about their concurrent force. We'll go to problem 9 by first going down to state 01, problem 9. This one is two problems. This splits here and there. This one has a torque spinning this way. It has to torque back. This problem you've seen over and over again. I'm not even sure how I laid this out when I did this here. So there is really no general processing here except for that distance, that if this is 10 and this is 5, this is going to push back with twice the force. And therefore this has to split back with twice the force, but it also has to be up, because indeed it needs to have reaction in the y direction only at this support. And I will finally go to problem 10. That one is literally all the force up has to be here, but there's a torque. This was 5 times, so it's far away, so you've got a 5 times the force there, but it's got to be reacting back this way because the sum of the force is 0. That is all the problems by slide and divide. Stay tuned for kind of a more logical way to do it, which is by moment arm.